Hello everyone, my name is Qi. I'm going to present our paper Strategies for MDP Bisimilarity Equivalence and Inequivalence. And this is joint work with Stefan Kiefer from the University of Oxford. The outline of the talk is as follows. I'll start with a motivating example, then I'll give you some definitions, preliminaries. Then we will focus on the two main problems of the paper, the bisimilarity problem and the bisimilarity inequivalence problem. Let's get started. So the two main problems are closely related to the notion of probabilistic non-interference from computer security. If you are not familiar with this notion, do not worry, as it is quite simple. So in concurrent programs, we have two types of variables, low and high in terms of their confidentiality. So the high variables, we want to keep them as secret and they are not observable. So I here give you an example of a simple concurrent program with just two Boolean variables, L and H. L, as their name suggests, L is a low variable and H is a high variable. So this program consists of just two instructions. L is assigned the value of H and L is assigned the value of not H. So we can represent the execution of this program as a diagram here showing on the slide. If the initial value of H is 0, then in the initial state it has like two options, two branches, depending on whether the first instruction or the second instruction is executed first. If we follow the left branch, the first instruction is executed first, then at the end we will observe that L has the value 1. On the other hand, if the second instruction is executed first, then at the end we will see L has value 0. Similarly, if H has value 1, then at the initial state it also has these two options. So to resolve the non-determinism, the options here, we can have a randomized scheduler to do that. A randomized scheduler example of it is like 50% of the time we execute the left branch and 50% of the time we execute the right branch. So if we think of the diagram for the execution of the program as a Markov decision process, MDP, then with such a randomized scheduler, a labeled Markov chain is induced. An example is shown here at the bottom of the slide. In this induced LMC, H0 and H1, these two initial states, are actually probabilistic bisimilar. We cannot distinguish between them. With a different randomized scheduler, saying that 60% of the time we execute the left branch and 40% of the time we execute the right branch, a different labeled Markov chain is induced. And in these induced LMC, H0 and H1 states, they are not probabilistic bisimilar. So we can distinguish between H0 and H1. Then this program is not safe as the value of the high variable H might be leaked. So if like the programmers, the good guys can control the randomized schedulers, we might want to ask to make sure that our program is safe whether there is a randomized scheduler such that the two initial states are probabilistic bisimilar. And in a second scenario, if like anyone can control the randomized scheduler, so to prevent the bad guys from stealing the secret values, we might want to ask whether under all randomized schedulers, the two initial states are always probabilistic bisimilar. So in the second scenario, it is equivalent to ask whether there is a randomized scheduler such that the two initial states are not probabilistic bisimilar. So these two scenarios correspond to our bisimilarity problem and the bisimilarity inequivalence problem. And before showing that the bisimilarity problem is expert time complete and the bisimilarity equivalence problem is MP, I'll give you some definitions. So the formal definition for the model labeled Markov decision processes labeled MDPs is like an MDP has a set of states and a set of actions, and each state has a label. In our examples, the labels are represented by the colors of the states. And there's a probabilistic transition function, which is a partial function, maps a state action pair to a distribution over the successor states. So to define strategies, we need the definition for a path in the labeled MDP. It is quite straightforward. So a path begins with initial states, then followed by action state pairs. Then a general strategy is just a function that maps a path to a distribution over the available actions of the last state in the path. A memoryless strategy, since without memory, so it's just a function that maps each state to a distribution over the available actions of that state. Then the second model is labeled Markov chain, LMC. So it's very similar to labeled Markov decision processes. The only difference is that in an LMC, every state has only one available action. And the most popular behavior equivalence for LMCs is called probabilistic by simulation. And it is an equivalence relation. For two states in this relation, they have to have the same label, and the probability from each of the two states to any of the probabilistic by simulation equivalence class E should be the same. And the probabilistic by similarity, denoted by tilde, is the largest probabilistic by simulation. So that's it for the models. Then let's talk about the bisimilarity problem. So in our earlier FSTTCS paper, we've already studied the bisimilarity problem is restricted to memoryless strategies. So in our first step, what we try to show is that maybe if there is a general strategy that can make two states probabilistic bisimilar, then this might imply there is a memoryless strategy such that the two states can be made probabilistic bisimilar by this memoryless strategy. However, as the MDP showing on the slide shows that this is in general not the case. So in this MDP, S state has like two actions, M1 and M2, and to make S and T probabilistic bisimilar, we can have like a general strategy to do that. It's very simple. So S first uses M1 action, then S uses M2 action, so then M1, M2, and so on. But if we only consider memoryless strategies, then the S and T in the induced LMCs will never be probabilistic bisimilar. It is quite obvious here. If we want S to mimic the behavior of T, so S needs to first choose M1 action so that it can immediately reach a green state. However, since we are considering memoryless strategies here, then S is restricted to use M1 action only. And in this case, S will never be able to reach a purple state. So S and T are not probabilistic bisimilar if we only consider memoryless strategies. But then we discover a game with attacker and defender. And with this game, we are able to show the expert time upper bound. So given a set, E, which is subset of the states, defender has a winning strategy for the game if and only if there exists a general strategy for the MDP, such that in the induced LMC, all states in E are probabilistic bisimilar. So I will show the idea behind of this game using this simple MDP. So we want to show that the two states S and T can be made probabilistic bisimilar. So we first add these two states to a set, and this is our current game state. then defender needs to provide us some evidence why these two states can be made probabilistic by similar. So firstly, defender needs to put the successors of each of the state in E to different sets. So for example, the U state, successor state of S is put into this purple set, and the V state of S is put into this green set. Similarly, for the state T, defender puts the V successor in the purple set and the W state into this green set. Secondly, the defender also needs to show that for every state in E, there is a local strategy such that the probability distribution from each of the state in E to the sets are like equal, are the same. So from S to the purple set, it is 0.3, then to the green set, it is 0.7. And also defender could show that there is a local strategy for T such that the probability to the green and the purple set is like 0.7, 0.3 respectively. So after that, attacker chooses the next game state among the sets that have been chosen by defender. So what happens here is that attacker is asking defender, if you are claiming that all these sets you've chosen can be made probabilistic by similar, then I will choose one of them for you to give me some evidence. And the defender wins the game if and only if it can be played forever. For example, if the next game state is this purple set, then defender has a quite easy job just to choose the purple state and put it into a singleton set. Then it can play forever. So the key thing here in this game is that the same state that can be reached from different paths actually can be put into different set. So here the V state reached from S actually is put into this green set, and the V state reached from T is put into a different set, this purple set. So the set of game states is at most the power set of the states of the MDP. That is to say that at most we will have like exponentially many game states. So with this game, we can show that there is a p-space bounded alternating Turing machine that accepts the bisimilarity problem. So the state space of the ATM, so alternating Turing machine, is divided into existential states and universal states, controlled by existential player and universal player respectively. So then the existential player just can take the role of defender, and universal player takes the role of attacker. So since alternating p-space is equivalent to x per time, we have that the upper bound of bisimilarity problem is x per time. So for the x per time hardness of the bisimilarity problem, we use the problem which is called the intersection emptiness of DTTAs. A DTTA stands for deterministic top-down tree automaton, and it consists of a set of states, a set of letters, alphabet, and also it has an initial state. What is special about this DTTA is that each letter has a rank, and it is used in the transition function. So the transition function is a partial function that maps a state and a letter to a sequence of states. And the length of that sequence is determined by the rank of the letter. So for example, if we have the rank of A0 is 2, then the transition function maps Q0 and A0 to a sequence of 2 states. So what we show here is that given k DTTAs, over the same alphabet, if the intersection of the language of these k DTTAs is not empty, then we can construct an MDPD with two initial states, and there is a general strategy for these MDPs such that the two states are probabilistic bisimilar in the induced LMC. So we show first that the intersection non-emptiness problem for DTTAs is expertime hard. And the proof is very similar to the proofs by Seidel on finite trees and the p-space hardness proof of the DFA intersection non-emptiness problem by Coulson. Then for each DTTA A1 to AK, we construct MDP D1 to DK, and we show that if the intersection of the language is not empty, then there is a general strategy for each of the MDP KMDPs such that the K initial states are probabilistic bisimilar in the induced LMCs. We are almost done here, but not yet, since in our bisimilarity problem, we need a single MDP with two initial states, but here we have K MDPs with K initial states. So with two extra states and some extra transitions, we are able to construct a single MDP with two initial states such that these two states, S1 and S2, are probabilistic bisimilar in an LMC induced by a general strategy if and only if for each of the K MDPs, there is a general strategy to make the K states probabilistic bisimilar. So now we have that the bisimilarity problem has lower bound expertime hard, and the problem is expertime complete with our previous upper bound. We also studied the bisimilarity problem for an MDP and an LMC. And this problem is easier. It's NP complete. To see why, let's think about the game with attacker and defender we introduced earlier. Then now the number of game states is limited by the number of states in the LMC. And the hardness proof is from the subset sum problem, which is NP complete. For our bisimilarity inequivalence problem, we also studied the problem with restricted to memoryless strategies, and we have that there is a polynomial algorithm to decide that in our earlier paper. So in our first step, we also try to show whether we can use our earlier result. As these MDP shows, we cannot. So these MDP, this state U, it has like two actions, M1 and M2. So there are a lot of general strategies can make S and T not probabilistic bisimilar. For example, if like we can let U choose M1 action if it is reached from S, and choose M2 action if it is reached from T, then in the induced LMC, S and T are not probabilistic bisimilar. However, when using memoryless strategies, since U is fixed to choose some local strategy, then S and T will always be probabilistic bisimilar. So, but here we can see the problem here, that is the same state reached from different path can use different local strategies when we consider general strategies. So what we try is like maybe we can have like two copies of the MDP. Maybe now it suffices to consider memoryless strategies for each of the two copies. And indeed, it is the case. With the help of an equivalence relation we defined, we call it super bisimilation. and this is like on the pairs of states on the two copies of the MDPs. And we show that for all general strategies, sigma and tau, the two initial states, S and T, S in the LMC induced by the general strategy sigma is probabilistic bisimilar to the T state in the LMC induced by the tau strategy for all general strategy sigma and tau, if and only if S in the MDP 0 copy is super bisimilar with the T state in the 1 copy. And in our earlier paper, we actually have a polynomial algorithm to decide super bisimilation. So we have that the bisimilarity equivalence problem is in P. All we need to do is to create two copies of the MDP. Then we can invoke the polynomial procedure for our bisimilarity equivalence problem. And for any positive instance of the problem, we can compute in polynomial time two memoryless strategies, sigma and tau, that witnesses S and T are not probabilistic bisimilar. To summarize, we studied the two problems, the bisimilarity problem, which is expert time complete, and the bisimilarity inequivalence problem, which is in P. We've also drawn the connection between the two problems with the notion of probabilistic non-interference from computer security. With that, I'd like to end the talk, and thank you very much for listening. If you have any questions, please feel free to ask. Thanks again.